Fibre optics and the fight against climate change. When light waves reflect off surfaces, they reflect according to the law of reflection. The angle of incidence equals the angle of reflection. What happens if the light isn't reflected and instead goes through the material? It bends. This is because of the different densities of different matter. The process is known as refraction. For example, let's compare what happens when light travels through glass and air. The glass is more dense than air, so when the light reaches the air, it speeds up and therefore bends. The incident angle is not equal to the refracted angle. Each material has what is known as a refractive index, which describes how fast light travels through it. A special case of this is when the incident light hits the boundary between the glass and the air at a special angle that causes the refraction angle to equal 90 degrees. The light travels along the boundary between the glass and air. This is called the critical angle. All light waves that hit this boundary at an angle greater than the critical angle will be reflected back into the glass again, following the laws of reflection. They are essentially trapped, reflecting off the glass boundaries. This is what's known as total internal reflection. Fibre optics are made of high-quality glass. They are flexible, thin rods not much thicker than a strand of hair. Fibre optics use total internal reflection to repeatedly reflect light, even when the fibre is bent, until it passes out of the other end. How can these fibre optics help in the fight against climate change? Aberystwyth University has taken part in a project that used fibre optic sensing to measure the properties of ice. The data was gathered from the ice cap in Greenland and is more detailed than any measurements obtained before. Greenland is covered in roughly 79% ice and is home to the second largest body of ice in the world. Climate change is causing the world's ice to melt. The mass of the ice from Greenland has decreased 6 times since the 1980s, making it the current largest contributor to the rising sea levels and therefore more important than ever to understand. Previous methods to study the ice cap would only attach about a dozen separate sensors onto the cable, meaning that measurements were very spaced out, with tens or sometimes even hundreds of meters between each one. The new technique uses fibre optic cables to transfer laser pulses from the surface of the ice sheet all the way to the base, which is a whopping 1,000 meters below. This means that the whole cable is essentially a sensor. These laser pulses gather highly detailed temperature measurements all the way along. The data gathered gives the scientists a better understanding of the movements of the Greenland ice sheet and can make more accurate models to help them predict its future movements, providing a useful tool in the ongoing battle to slow down the effects of climate change. The research for this project was led by the University of Cambridge and part funded by the European Union. Professor Bryn Hubbard and Dr. Samuel Doyle from Aberystwyth University led the team of scientists that drilled the borehole in the glacier.